Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to answer a question that was asked by one of my subscribers. He said to me that I came across a geometric and harmonic means, which are very interesting concepts. Would you mind making a video about the geometric mean, sir? Okay, so that's what I'm going to do very quickly, as best as I can, given that I've just recovered from my voice loss, and I feel that now is as good a time as any. So let's begin. Now, in my applet, which I will give you a link to this download. So it seems I got cut off. Anyway, let's begin again. So I was asked a question by one of my students, as I showed you here, to make a video on the geometric means, and seeing now that I have my voice back and I'm able to do it, I'll try to do it as quickly and as well as I possibly can. So excuse me. As you can hear, my health is not very good. So, what are means and their measures? Well, I'm going to quickly discuss these three means with you. So, really, the arithmetic mean is the first type of mean, which was never mentioned by the ancient Greeks, but it's pretty obvious that they must have understood it, because they defined area as a plane number, and a plane number is a product of two arithmetic means, even though they didn't say as much. So when does an arithmetic mean make sense? It only makes sense when the values can be redistributed. So if you have, for example, 1, 2, and 3, then you can make all these equal through redistribution. And all you have to do is one redistribution. You take 1 from 3 and add it to this one, and then you have all 2's, right? So that the mean becomes the same. And why does the mean become the same? Because if you add these up, it will equal to the side here when they're all the same. So that's really what the arithmetic mean about, is how to make a set of values equal through redistribution, not the nonsense that you hear your math teachers and professors tell you. They've never understood a mean. Incidentally, every number is also a mean, okay? Because every number is defined as a ratio. And a ratio has an antecedent and a consequent part. And if you read my article on how we got numbers on LinkedIn, you'll find more about it. You'll find out more about it. So the geometric mean is a mean that only makes sense when a relation exists between a range of numbers. That relation might also happen to be a function. So if you look at this particular triangle in a circle, which rests on the diameter of the circle, this red line here is equal to the square root of the product of these two line segments, okay? And it's expressed as you see here. Altitude of x is equal to this function. And it's very easy to prove. The proof is done by similar triangles, okay? And this red line over this blue line is equal to this light blue line over this purple or magenta line, okay? And this is from the theory of similar triangles. And also from the theory of similar triangles, you can prove the Pythagorean theorem, okay? So you don't need Pythagoras to prove similar triangles. Why are these two triangles similar? Because these two angles rest on the same arc, and these two angles rest on this arc, and these two angles here are vertically opposite, okay? So you can say that the geometric mean describes the measure of any given set of values in terms of their product. And of course, if you had to consider a sphere and look at this as a type of oblique prism in the sphere. It's not going to be a prism exactly because the sphere has circular arcs. Then you will also find out that you can get a geometric mean in the power of 3. Okay, so really, if you have that, then it will be the third root of the product of this line, and the one that goes across on the prism. Okay, so if I don't know if I can do this with my mouse, but let me see if I can use Sketchpad like this. Maybe not like that. I want to actually draw on the screen. So let me see if I can do that. So if you had, if you were able to, let's see if I can do that. Yeah, extend that triangle like that. Of course, I'm not drawing it exactly correctly. And then also this line here, like so. Okay, and then like that, and like that. And of course, within the circle, you can find the third power of the geometric mean. Okay, so at any rate, I don't want to spend too much time on that. So this, by the way, this is a special presentation, as I mentioned at the beginning of my video. It's very hard for me to breathe, so I'm having to pause every now and again. It's a young French student, I think, who's translating my free ebook, and this is a special favor for him. Now, the harmonic mean is also a special kind of mean and only makes sense when a reciprocal relation exists. Okay, so what is a reciprocal relation? It's one in where the mean consists of ratios as you see over here, and the relationship is defined in terms of these x1, x2, and xn. So an easy way to see it is by looking at the resistance in series. So this is the resistance in series, and obviously the resistance in parallel will be this. Incidentally, any mean is really also a harmonic mean, because if I the only difference being that the denominator has a sum of ratios, whereas in the case of the arithmetic mean, usually the numerator has a sum of ratios, because 1, 2, and 3 are also ratios. Yes. Okay, so this is an example of where it occurs in nature or in electrical engineering, which is nature, because we're part of nature, aren't we? Okay, and there's a reason that this relationship exists. So ultimately, we're looking only at a harmonic mean when a relation exists between a range of numbers, and the same thing for the geometric mean. The difference between the geometric and the harmonic is that with the harmonic, all the values are included in the relation at once. Okay, so the whole omega 1 through to omega n are included, whereas maybe in a geometric mean, you can take the mean of omega 1 and omega 5, but as you can see, that doesn't make much sense also doesn't make much sense also because in the geometric mean you also need a relation, and for this very reason, that if one had to take the geometric mean between 2004 and 1 million, it really is completely senseless. Now, you will notice that this sort of thing will appear in statistics, and this kind of looks or gives a hint of the variance statistics, the variance statistic in the topic of statistics, because the variance is normally sigma squared, right? And the standard deviation is sigma. Okay, these are not exactly the same, but they're similar in certain respects. And so this here is a very quick introduction to the geometric harmonic means. I'm sorry I couldn't do it a lot better. I would probably be able to summarize it into half the time if I wasn't so unhealthy and able to speak properly. And so anyway, I hope you've learned something from this. And to this French student, if you have any more questions, feel free to contact me. My email is at the bottom of my new calculus page, and I'll put a link to this applet as well as the How We Got Numbers article on LinkedIn and anything else that I think might help you to understand this better. I'm looking forward, young man, to your translation of my free ebook in French. That is going to be very exciting, and I shall place a link to it on my website once you've completed it. Know that I have 3 translations of my free ebook already. And also I have a young man in Greece working on my ebook translation into Greek. Well, that's pretty much it for now. My name is John Gabriel. This is New Calculus. Wish you all well during this very terrible time, and stay safe. Till next time, goodbye.